Okay, folks, so today we're going to begin work in Chapter 6, and this is essentially the beginning of the second half of the course, where we began understanding what an antiderivative is, and how to find it, and what its applications are. So let me ask you to consider the following diagram. So what we have here is a velocity versus time graph. And let's suppose the question here, and notice that the velocity is constant at 50 miles an hour, which makes this to be a pretty simple example, but it'll help to lay the groundwork for what's to come. And so let's suppose the question is, how far have we gone in the first 2 hours? Now you all know that if you're going 50 miles an hour for 2 hours, you happen to go 100 miles. But what I'd like you to see is how that is a piece of this graph. So if I draw a line right here, and I think about that area, well, that area is the base, 2 hours, times the, the base is 2 hours, the height is 50 miles per hour, and so what we notice is the hours cancel, and we wind up with 100 miles. And so the area under this curve, because it's base, which is time, times the height, which is velocity, and we know that distance is equal to rate times time, the area under that curve actually gives us the answer to the question, which is how far do you go? So what you begin to get at here, just beginning, is how important it is to find the area under a curve. And as we move on in this chapter, you'll understand how we can find the area under a curve exactly. The next example will help you see how we can approximate it. So here's a more interesting, a more realistic idea. What we have is the same idea, the velocity versus time, and the question is the same. How far have we traveled as we go from time A to time B? Now, you should believe, based upon what we have just done, that the distance traveled will be the area under this curve. The trouble is, how do I find the area under that curve? So, one of the things that we can do is kind of break this interval up, say, into 4 pieces. And for each piece, what I'll do is something similar to what we did on the first example. What I want to do is draw a rectangle. Now I can pick 3 ways of drawing this rectangle, and you'll see examples of that in a second. I can choose as my height for the rectangles the left-hand endpoints, 4 of them, or the right-hand endpoints, or I can find the heights at the midpoints. We'll never do that, but it is discussed, and so you should be aware of it. So in this case, let's draw the heights using the height at the left-hand point. So it'll look something like this. Get it? And for each of these rectangles, I can find the area. And in each case, the area will simply be an approximation for how far we traveled over that time interval. Now, if I wanted to, let's see, what's a nice color? Let's try this one. Here's what the rectangles would look like if I picked my right-hand endpoint. Similar, but not exact. And so the question that you should ask here is, what can I do to make this be a better approximation for the distance traveled? And the answer would be, let's use more rectangles. Let's use 8 rectangles. Let's use 16 rectangles. Let's use a lot of rectangles. And you should believe that the more rectangles you use, the better the approximation is going to be to the area under the curve. And in this case, it's again important to notice that the area under the curve is what we're looking for, which is the distance traveled. So just to kind of give some language to these points, what you have here are pictures of rectangles under a curve. And what we want to do is distinguish one from the next. So the first one is what we call LRAM, which stands for Left Rectangle Approximation Method. The next one is MRAM. That's the one we'll never use, but that's using midpoints as the heights. And the last one is RRAM. And so the ones that we will make frequent use of to approximate the area under a curve is LRAM and RRAM. Okay, so hopefully this example will help drive these ideas home. So this is about as simple as we can make it. Let's consider a function f of x equals x squared. We want to approximate the area under that curve from 0 to 4 using 4 rectangles. So on the left, we'll use LRAM, using as the height the left-hand endpoints. Notice here the rectangle is flat. And over here we'll use RRAM, where we're using as the height the right-hand endpoint. And in each case we want to get an expression for what the approximation for the area under the curve. So for LRAM, we noticed that the base of each rectangle is 1. That made it as easy as we could. The first height is f of 0. The next height is f of 1, and then f of 2, and then f of 3. So putting in the values for f of x equals x squared, here's what we get. And so using LRAM, we get 14. And if you look at the graph, you should believe that this is an underestimate. The actual area is more than that. And so when we look at RRAM, we're using right-hand rectangles, and we get each of the bases is 1, so it's 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4, and that comes out to be 30. So this is an overestimate, and you can see up here, these are all the ways in which it's more than the actual area. So this is a pretty gross example, in the sense that, my left rams give me 14, my right rams give me 30, and the exact area is somewhere in between 14 and 30. Now, you should believe and understand that if instead of 4 I used 8, this number would be bigger, this number would be smaller. If instead of 8 I used 16, again, this number would be bigger, this number would be smaller, and they would begin to meet in the middle, and the middle in this case would simply be the exact area under the curve. So in our next lecture we'll begin to look at how we really and truly get that exact area. But for right now, we're just concerned with using rectangles, using finite sums to approximate the area under the curve.